Hello coders, I welcome you all. Today we are going to understand one of the most important concepts in cybersecurity and network security, that is cryptography. If you do not understand the complete flow in the first attempt, don't you worry. Watch the explanation multiple times and try to write the complete flow step by step using pen and paper. Once you draw the flow yourself and connect each step, concepts like encryption, hashing, digital signatures, verification, and certificate authority will become much easier to understand. So let's get started. Whenever you use the internet for online banking, WhatsApp messaging, email communication, UPI payments, cloud storage, or any secure website, a very important question arises. How can we securely send information over an insecure network like internet? We must ensure that only the correct person can read the message. The message is not modified. The sender is genuine, and both users can trust each other. To achieve all these security goals, cryptography is used. So instead of learning every concept separately, today we will understand the complete cryptography flow through one simple connected example using Rahul and Neha. Suppose Rahul wants to send a secure message to Neha through the internet. So here in this scenario, Rahul is the sender and Neha is the receiver. In this example, we are going to use asymmetric key cryptography, also called as public key cryptography. There are multiple algorithms available for asymmetric key cryptography, such as RSA, Diffie-Hellman, elliptic curve cryptography. These algorithms are separately designed to work with public and private key pairs. Any of these algorithms can be used depending on the application and security requirements. But in this example, we are not focusing on a specific algorithm implementation. Instead, we are understanding the overall concept of public and private keys and how they are used to achieve confidentiality, integrity, authentication, and trust in secure communication. In asymmetric key cryptography, every user has two keys, a public key, which can be shared with anyone, and a private key, which is kept secret. So Rahul has these two keys, public and private, which are represented by R public, Rahul's public key, R private, Rahul's private key, and Neha has also these two keys, public and private, which are represented by N public, Neha's public key, and private, Neha's private key. So using this example, we will understand confidentiality, integrity, authentication, non-repudiation, digital signatures, hashing, certificate authority, and the complete verification process step by step. So let's start with the first question. How can Rahul send a secret message to Neha securely? So first, let's understand normal encryption. Rahul creates the message, hello. Now Rahul wants to send this message securely to Neha. To keep the message secret, Rahul encrypts the message using Neha's public key, means using receiver's public key. To keep the message secret, Rahul encrypts the message using Neha's public key, means using receiver's public key. Here you can see encrypt M, comma N public. M is the original message, hello in uppercase, right? N public is the Neha's public key. So now here, C, which is ciphertext, which is created using Neha's public key. So as I said, Rahul encrypts the message using Neha's public key, means receiver's public key. Now Rahul sends the ciphertext C through the insecure network to Neha. At Neha's side, means at the receiver side, Neha uses her private key to decrypt the message that you can see here. Decrypt C, N private. C is the ciphertext or encrypted message, and private, which is Neha's private key. So at the receiver side, means at the Neha's side, Neha uses her private key to decrypt the message. Since only Neha has her private key, only Neha can decrypt and read the message. This is normal encryption. So this achieves confidentiality. because only Neha has the private key required to decrypt and read the original message. But now an important question arises. But before that, please recall how normal encryption is performed. Rahul encrypts the message using Neha's public key and Neha decrypts the message using her private key, right? But Neha's public key is publicly available. That means anyone can use Neha's public key to encrypt a message and send it to Neha, right? So Neha receives many encrypted messages, but Neha is only expecting a message from Rahul. So the question is, how can Neha identify that the message is really from Rahul? This means encryption alone provides confidentiality, but it does not provide authentication, right? So now we need digital signatures. So now let's continue the complete secure communication flow. So let's start from scratch. Now Rahul again creates the original message, hello. Now the first question is, how do we ensure that the message is not modified during transmission? For this, Rahul creates a hash using the original message, hash, and here Rahul passing original message, hello. This means the hash function takes the original message M as input and generates a fixed size hash value H. This hash acts like digital fingerprint of the message. If even a single character changes in the original message, the hash value will completely change. So this step ensures integrity, meaning the message has not been altered. Now we have hash, right? Now the next question is, how do we prove that the message was originally sent by Rahul? For this, Rahul creates a digital signature using his private key, means using sender's private key that you can see here. Sign H, which is hash value, which is already we generated, right? And R private, which is Rahul's private key. So here the hash created from the original message is signed using Rahul's private key. So please remember here the hash value created from the original message is signed using Rahul's private key. In simple terms, we can say like this: the signed or encrypted hash becomes the digital signature. This property is called authentication. Also ensure non-repudiation, meaning Rahul cannot later deny that he sent the message. Now finally, Rahul combines the original message and the digital signature that you can see here. We have created hash. From hash, we created digital signature. Now finally, Rahul combines the original message and the digital signature that you can see here. Message plus signature. Data is equal to M plus S. And now we have this final data, which is M plus S. Now another question arises. How do we keep this complete data secret while sending it to Neha? Now normal encryption that we did before, right? For this, Rahul encrypts the data using Neha's public key, means using receiver's public key, like this, right? We just discussed. So here in place of M, we have to put data, because data is equal to M plus S, right? So now all done. Our data is encrypted. So as you know, encryption ensures confidentiality because only Neha can decrypt it using her private key. All done. Now another question arises. How does Neha trust that the public key really belongs to Rahul? Please listen it carefully. This verification is very important because Neha will use Rahul's public key to verify the digital signature, because as we just discussed, Rahul creates a digital signature using his private key. So Neha will use Rahul's public key to verify the digital signature, right? If the public key does not actually belong to Rahul, an attacker could use a fake public key and impersonate Rahul. So before verifying the signature, Neha must first ensure that Rahul's public key is genuine. For this, Rahul attaches a digital certificate which is issued by a certificate authority. This provides trust in the communication. Now Rahul sends this C plus certificate. Here C representing our data. This data is equal to M plus S, right? So now Rahul sends the encrypted data along with the certificate to Neha. So data plus certificate. Now let's move to Neha's side. Before we move to Neha's side, here is the important note that you can see here. The certificate is generally not encrypted because it contains Rahul's public key and identify information required for verification by Neha. Now we have done all from the sender side, means Rahul's side. Now let's move to Neha's side, means receiver side. The first step is decryption. So as you know, data is already encrypted by Neha's public key. So Neha uses her private key to decrypt the encrypted data that you can see here. So now Neha gets what? Data is equal to M plus S. Message plus signature, right? So here the original message is M and the digital signature is S. Before verifying the digital signature, Neha first verifies the certificate using the certificate authority. This ensures that Rahul's public key is genuine and really belongs to Rahul. All done. Certificate verification is done. Now Neha verifies the digital signature. First, Neha uses Rahul's public key to verify the signature like this. Signature plus Rahul's public key. This means Neha uses Rahul's public key to recover or verify the hash value from the digital signature, right? This is possible because the digital signature was created using Rahul's private key. In simple terms, the hash was signed or encrypted using Rahul's private key, so it can be verified using Rahul's public key, right? Now we have H1, hash recovered from the digital signature, which is H1, means Neha obtains the hash value from the digital signature using Rahul's public key. So step 1 is done. Now next step, Neha independently recomputes the hash from the received original message. You can see hash and M that we are storing in H2. So now Neha has H1 and H2. H1 means has recovered from the digital signature and H2 means newly generated hash from the received message by Neha. Finally, Neha compares both hash values. H1 is equal to H2. If both values are equal, it confirms that the message has not been modified during transmission, ensuring integrity. The message is genuinely sent by Rahul, ensuring authentication. Hope all of you are clear with end-to-end flow. Now let's summarize everything. So first, Rahul creates the original message. Then Rahul generates a hash from the message to ensure integrity. After that, Rahul signs the hash using his private key to create the digital signature. In simple terms, the signed hash becomes the digital signature. Now Rahul combines the message and the digital signature, so data is equal to M plus S. Then Rahul encrypts the complete data using Neha's public key to achieve confidentiality. Then Rahul also attaches a digital certificate issued by the certificate authority so that the Neha can trust Rahul's public key. Now the encrypted data with certificate travel through the insecure network, means through internet. At the Neha's side, she first decrypts the data using her private key. So Neha receives data is equal to M plus S, means M plus S. Then Neha verifies the certificate using the certificate authority to confirm that Rahul's public key is genuine. After that, Neha verifies the digital signature using Rahul's public key and recovers the hash value from the signature. Next, Neha independently generates a new hash from the received message and compares both hash values H1 and H2, right? If both hashes match, the message is not modified, ensuring integrity, and the message is genuinely from Rahul, ensuring authentication. So you can see this simple flow demonstrates confidentiality through encryption, integrity through hashing, authentication and non-repudiation through digital signatures, and trust through the certificate authority. This completes our entire secure communication flow using asymmetric key cryptography. Hope you like this. Let's move on.